Hello everyone, welcome back to online lecture series on design of machine elements. This is our third lecture on pressure vessels. So in our last lecture we had discussed about the thick cylindrical shells subjected to an internal pressure. So for this we use the Lam's equation in which we have obtained the maximum tangential stress and minimum tangential stress. So now we will move forward with our radial stress, the maximum and minimum values of radial stress. So we will be utilizing this formula again. This formula which we have already uh, obtained. So here let's begin. Let me write down that equation again. Sigma r is equal to P Ri square divided by, we can also check it from here, Ro square minus Ri square into 1 minus Ro square upon x square. So in our previous lecture we had discussed that this radial stress will be maximum at the inner radius and minimum at the, that is 0 at the outer radius. So we will do the same over here, that sigma r is equal to sigma r maximum when x is equal to r I. So let's put this. Over here, so sigma r maximum will be equal to P R I square minus divided by Ro square minus Ri square 1 minus Ro square divided by Ri square. Now once we simplify this, what we will be getting here is minus P Ri square divided by Ri square into Ro square minus Ri square divided by Ro square minus Ri square. So here we will have the final answer as minus P, which is compressive. So this is sigma r maximum. Now let's discuss about minimum one. So sigma r is equal to sigma r minimum when x is equal to Ro. So applying these conditions over here, then what we will be getting, sigma r minimum is equal to p r I square upon r o square minus r I square into 1 minus 1. So this will go as 0. Is equal to 0. So I hope you are getting this. Now we can copy this part. So now we will move forward with the thickness. First of all, we will evaluate the thickness of this thick cylinder for the brittle materials. So for that we will be using maximum normal stress theory. Okay, so based on that we have already obtained this kind of formula that is available over here. So we will be utilizing this equation only. So let me write down the same equation again. Sigma t is equal to sigma t max is equal to P into RO square plus RI square divided by RO square minus RI square. So this is the equation that we are going to focus on, and here instead of RO we will put Ri plus T. So let's do this. So here implies that sigma T into Ri plus T square minus sigma T Ri square is equal to P into Ri plus T square plus Ri square. So now the next simplification will be sigma T minus P to Ri plus T square is equal to Ri square into sigma T plus P. So here we need to evaluate the thickness. So for that, Ri plus T square is equal to Ri square. I think we can take this on here in the denominator, divided by Ri square sigma T plus P divided by sigma T minus P. So implies that 1 plus T upon Ri is equal to square root of sigma T minus plus P divided by sigma T minus P. So again, T is equal to Ri into square root of sigma T plus P divided by sigma T minus P minus 1. So this is the value of thickness for brittle thick cylindrical shell. So now we can copy this. Now we will follow the same thing again for the ductile materials. For ductile materials, what we will use here is maximum shear stress theory. So here we will be using maximum shear stress theory. So what does this theory say? That the maximum shear stress, so let me write down so it will be much easier for me to tell you. Just wait. Maximum shear stress at any point in a strained body is equal to 1/2 of the algebraic sum, difference between maximum and minimum principal stresses at that point. So this is the principle that we are going to follow. So let me copy this over here. Okay, we will keep it over here only, so you can read it if you want to. Maximum shear stress at any point in the strained body is equal to 1/2 of the algebraic difference between the maximum and minimum principal stresses at that point. So we will utilize this principle over here. So for that, first of all, we need to write down the maximum and minimum stresses. So sigma T maximum is equal to P into R O square plus R I square divided by R O square minus R I square, and sigma T minimum is equal to minus P. So let me remind you that we have already obtained these formulas in our previous derivations. So now we will obtain the maximum shear stress based on that theory. So tau is equal to tau max is equal to sigma T max minus sigma T minimum divided by 2. So here what we will achieve out of this, P divided by 2 R O square minus R I square into R O square plus R I square plus R O square minus R I square. So what we will be achieving out of this? This 2 will get cancelled. So finally we are getting here P into R O square divided by R O square minus R I square. So this is the value of tau max, or we will simply keep it as tau. However, we can now further modify this equation to include the thickness T, Ri plus T whole square divided by Ri plus T whole square minus Ri square into tau. So tau into Ri plus T whole square minus tau Ri square is equal to P into Ri plus T square. So here, further simplifying this equation, so tau minus P into Ri plus T square is equal to P plus tau into Ri square. So So again 1 plus T upon Ri is equal to tau plus P into divided by tau minus P and whole square root. So now T is equal to Ri into square root of tau plus P divided by tau minus P minus 1. So this is the equation of thickness. This is T. Now generally tau is equal to sigma T divided by 2. So we can modify this equation as T is equal to Ri sigma T. I think have we made any mistake here? Let me see. So here there is one mistake is over here, that here only we will have tau. Only tau will be there. You can check it by yourself that only tau will come. So here it will be sigma T divided by sigma T minus 2P minus 1. So this is the thickness that we have obtained. So this was a bit longer derivation. So the same equations are also written over here. So if you want to note down them, you can pause this video at this moment and you can write down this. So now we will move forward with our next theory, that is Bernoulli's equation. Now these are just standard equations which are given as they are. So in case of open end cylinders such as pump cylinders, rams, gun barrels, etc. are made of ductile material like low carbon steel, brass, bronze, and alloyable aluminum alloys. In such cases, the allowable stresses cannot be determined by means of maximum stress theory of failure. So for that case, maximum strain theory is used. So you need to remember this, that in case of open end cylinders which are made of ductile material, in this case we use maximum strain theory. According to this theory, the failure occurs when the strain reaches the limiting value, and Bernoulli's equation for the wall thickness of the cylinder is given by this formula. So we don't have any kind of derivation like this, so we will simply accept this formula as it is given. Okay, so this is the Bernoulli's equation which is used for the ductile material by which open end cylinders are made, where we use maximum strain theory, and the wall thickness equation is this. Now the next is Claverino equation. This equation is also based on the maximum strain theory of failure. Okay, however, it is applicable to the closed end cylinders, that is the cylinders which are fitted with heads made of ductile material. Now according to this equation, the thickness of cylinder is given by this formula. So this formula is just given as it is, there is no proof for this. So you just need to remember the formula. So our next theory is compound cylindrical shells. However, we will continue this theory in our next lecture. So what we have done today, in our today's class, we have discussed about the thick cylindrical shells which are subjected to internal pressure, in which this is the thick cylindrical shell in which we saw this tangential stress distribution and radial stress distribution, and then these are the nomenclatures. We use the Lam's equation. This is the first equation is tangential stress, and this is the radial stress. So the value of maximum tangential stress and minimum tangential stress. Then again also we have maximum radial stress and minimum radial stress. After that we obtained the thickness for the brittle material using the maximum normal stress theory, and the thickness for the ductile materials using the maximum shear stress theory. So these are the final equations that we have arrived. And then we saw the Bernoulli's equation and Claverino's equation. So that is the end of today's lecture. So that is the end of our third lecture, and we will now move to the compound cylinders, which is our last topic of this chapter, compound cylindrical shells. As you can see, how many topics we have already covered. See, in this chapter we have completed introduction, classification, stresses, that is circumferential or hoop stress and longitudinal stress. Then we discussed about the thin cylindrical shells subjected to internal pressure and thick cylindrical shells subjected to an internal pressure, in which we have discussed Lam's equation, Bernoulli's equation and Claverino's equation. Now the last two topics are compound cylindrical shells and stresses in the compound cylindrical stress. So this topic will be done in lecture number 4, and the last topic will be completed in the lecture number 5. So that's it for today. See you in our lecture number 4 of this pressure vessel series. Thank you for watching this video.